recovery. Together with this, I will also be looking at the treatment of effluent water deriving from textile industry. So before I proceed into this presentation, I welcome everyone on board. And if you do have any questions, please write the questions into the Q&A section, and we will try to answer your questions at the end of this presentation. If not possible, we will also forward you some answers later on following this presentation. So across this presentation, I'll be talking about a number of topics. First and foremost, I'll be giving you an overview of PCI's membrane portfolio. So talking you through all the different types of membrane that we have available. And then I'll be talking about the dye and dye desalting. So basically looking at the definition and classification of dye, and also talking about reasons and advantages of completing dye desalting. Then I'll be talking about the applications of nanofiltration and ultrafiltration membranes in textile dyeing applications. So looking at liquid dye production via nanofiltration and the ultrafiltration process, and as well as talking about grain on solid dye production with the nanofiltration or ultrafiltration membrane. Then I'll be talking about dye filtration within the dye industry, giving you examples of dye filtration water requirements for dye applications, and also talking about water recovery following the dye filtration process. Following this, I'll also be talking about giving you an overview of the percentage of dye loss with dye filtration in relation to the type of membranes that has been used. I'll also be presenting the process variation with dye filtrations. And then at the end of this presentation, I'll be talking about textile wastewater applications. So basically looking at how we could recover COD and color remover from the wastewater just to be able to comply with some local regulation. So with regards to the first part of the presentation, so to talk about PCI's portfolio with regards to the type of membrane that we can supply to you for any sort of application that you have. We have a number of membranes available on the market. As most of you might not know, PCI is mainly known for tubular membranes, but at the same time, we are also known for supplying spiral and hollow fiber membranes. So I'll be talking you through all of these configurations over this presentation. So starting from the bottom, we have the microfiltration membrane, which is basically the most open membranes that we have on the market. So talking about the LMAO2, which is based on 0.2 microns pore size. So then moving forward across a number of ultrafiltration membrane from LP450 to CA202. So basically moving around the 450,000 Dalton to 2,000 Dalton membrane type, to then moving across the nanofiltration membrane. So basically looking at AFC 30, AFC 40, basically talking about 200 to 250 Dalton for the AFC 30, and then looking at AFC 40, why we are talking about basically around 300, 350 Dalton for the AFC 40. So then talking about the AFC, the reverse osmosis membrane, so basically AFC 80 and AFC 99. The classification between the nanofiltration and also the reverse osmosis could be done in accordance to the rejection of salt. So for the AFC 99, we are basically talking about 99% sodium chloride rejection. For the AFC 80, we're talking about at least 85% sodium chloride rejection. We can use the same classification as well for the nanofiltration, in which case, for the AFC 30, we are looking at least 75% calcium chloride rejection. For the AFC 40, we are looking at 60% sodium chloride rejection. So all these membranes could be classified into a number of configuration, for which we call the A series. So basically looking at the loose tubes. We also refer to the B series, in which case we're referring at the tubes which are inserted into a housing, a B1 housing. Then we have the C series, which of course refer to the membrane tubes, which are also inserted into a housing. In this case, inserted into a plastic housing in ABS. So the other classification could be based on the pressure limitations on this membrane type. For the A series, we're looking at low pressure applications. So basically around the 7 bar for the loose tube, which are supported at each end with epoxy resin, and then inserted into a housing. In some cases, it might be stainless steel. For the A5, A19, A37, and then we might also have a housing in GRP for the A8. For the other case, we have the C series. Of course, this is mainly used for water applications, in which case the housing is in ABS, and the pressure could be rated up to 12 bar. Then we have the B series, which of course incorporated into a stainless steel housing, for which case we could take the pressure up to 64 bar. And in some instances, if the application is required, this could also be taken to 80 bar. But for this case, we need to use a specific housing, which could take up to the 80 bar range. So beside the previous membrane types, we also have the so-called classic membranes. So the classic membranes are also tubular, as well as the porous TMF modus. So the classic membranes are available in diameters that range between 11 millimeter to 25 millimeter, and they could be taken up to 6 meter length. For the previous membrane that I've discussed above, the range, the top length could be up to 3.6 meter length. So when talking about the classic membrane, we have options available between the ultrafiltration and also reverse osmosis, with molecular cutoff between the 50,000 Dalton to 550 kilodaltons. And then we also have a reverse osmosis available for this type of configuration as well, which has a sodium chloride rejection in the region of 95%. But then when we're talking about the porous tubular polymeric filters, these are available in PVDF membrane, and they could be bonded to a PVDF or PE substrate. The porous TMF modus, as well as the classic membranes, as well as the previous tubular membrane that I've discussed about, they have a very open channel, which allow them to be suitable for high solid applications. With regards to the porous TMF modus, the pore size options are based on 12.7 or 25.4 millimeter. We have a number of pore size in terms of the molecular weight cutoff around the 0.1 to 0.02 microns. And also, this membrane could be supplied in various lengths, either 0.305 or 1.829 meters. And then they could be configured into a number of membrane tubes to form a module. The maximum that we have available is in the region of 61 tubes, obviously giving a higher membrane area. So the porous TMF modules also have the advantage of being able to be subjected to back pulsing. What that means is that these modules could be backwashed by supplying a certain amount of air into the permeate side, which pushes the permeate flow backward and help to reduce the impact of fouling on the membrane layer. So this is one of the advantages of using the porous TMF together with the open tube diameter, which allows the membrane to undo a high solid concentration. Then another product available from PCI portfolio is the FG spiral core membrane element. We have a number of options ranging between the ultrafiltration to nanofiltration to reverse osmosis. And these membranes are being built with high-tech membrane technology, which obviously help to have a spiral core element, which is able to withstand some operating conditions that are not familiar to other competitors out there. Beside the spiral membrane technology, we also have hollow fiber membrane available as part of our membrane portfolio. These are typically available in the range of 0.02 microns. And we have two options, which is the ZMBR or the GMBR, both of which are reinforced submerged hollow fiber membranes available. So all of these are the membranes that we have available as part of PCI portfolio. And I'm sure I'll be talking about the applications of some of these membrane within the dye processing later on in this presentation. So coming back to dye, in this part of the slide, I'll be giving you the definition and also the classification of dye. So how can we define a dye itself? A dye can be defined as a coloring material which is used to impart color to different substances. So basically talking about fibers, cotton, and so on. And this is possible through a chemical binding to the substrate to which the dye is being applied. I'll be talking about the source of dye. As we all know, dye could be produced either chemically, which is what we call synthetic dye, or dye could also be available in nature, natural dye. So before I move into the classification, I'll be talking about what makes up the dye molecule itself. This is mainly consisting of three chemical groups. So we're talking about the chromogen, which is mainly together with the chromophore, are the groups that are responsible for the color in dye itself. So dye is mainly formed through the combinations of hydrocarbon, so mainly talking about benzene, naphthalene, paraffin, together with solvents, as well as in the presence of acid or alkaline solution, to then formed via a number of reactions to produce the dye itself. So the chemical groups which we're talking about at the moment is the chromogen. So talking about the aromatic intermediates, so benzene and naphthalene, which is then combined with the chromophore, which is the color-giving group. So basically talking about the nitro group or the azo group, as well as the sulfur group. So then talking about the oxochrome, which is basically the salt-forming radical group, which are mainly responsible for the covalent properties of the dye, as well as responsible for the stability of the dye. So these are the three main chemical groups that form a dye. So to talk about the classification of the dye, this can be classified based on the source. So as I explained earlier, we can classify a dye based on the natural origin. So a dye could derive from the roots, from berries, from bark, leaves, wood, and so on. But also, most of the dye that are currently being used in the industry are synthetic dye, so basically coming from petrochemical origin. Then dye could be classified based on ionic nature. So basically talking about anionic, so negatively charged dye. So looking at reactive dye, which is going to be one of the main focus from this presentation, and is one of the main dye type that's mainly used within the industry. This is mainly due to the covalent properties of the dye to bind to the substances to which it's been applied. Then the classification could also be done based on the cationic dye, so basic dye, or non-ionic dye. Then dye could also be classified based on chromophoric group, so talking about azo dyes, indigo dyes, and so on. But then it can also be classified based on the chemical structure. So we could look at water-soluble dyes. So the most important part of it is the reactive dye. There are also directive dye, acid dye, and so on. But then there are also water-insoluble dyes. So talking about VAT, sulfur dyes, and many others type of dyes. So the next part is to talk about the reasons and advantages of dye desalting. It is important to understand what makes up dye itself. So salt is one of the main components in reactive dye manufacturing process, and the classification is based on having, let's say, 60% dye, 20% formulating agents or dispersants, 15% inorganic salts, and 5% moisture. And with regards to how the dye final product could be marketed within the industry, this could be marketed either in a liquid form, so having a desalted and concentrated dye, or it could be marketed in a solid or granular form, which is mainly obtained from the liquid dye via spray drying. So why should we perform dye desalting? Normally, when having dye in a liquid form, they could become unstable when stored. This is due to the presence of salts, if not desalted, and also it can precipitate some of the components if the salts are not taken out, and this could lead to having a structurally weakened dye. So that's one of the reasons why dye should be desalted. And the advantage from desalting a dye by using membrane technology could be related to improving the final product of the dye, as well as increasing the quality and the yield from the production process. So we perform desalting to kind of help to have a more stable and prevent the precipitations of the major component that form a dye. Another advantage is to produce a more consistent dye product, which could then be processed to form a grain or solid dye through spray drying. So this allowed to get a more robust grains and also having a final product with higher strength. So by implementing membrane technology to perform dye desalting, it is also possible to improve the efficiency of the spray dryer when producing a solid grain dye type. This means that the final grains are less dusty and more granular. And also, this also helps by removing the salt from the dye solution. It also helps to prevent the incrustation of the spray drying nozzles, which of course could lead to process downtime if this were not removed. The other benefit is that we are able to have an effective control on effluent color and impurities prior to discharge from the solution. So this part of the presentation is to give you an overview of liquid dye production via the use of nanofiltration or ultrafiltration membranes. Of course, the production of dye happens towards a number of reactions, a number of processes, which includes using the reactor, for the blendings of the major components of the dye, from the hydrocarbon to either using the acid or alkaline solution together with the sulfur or nitrogen reactions in the presence of solvents. This is then passed through a number of processes, which might include the press, fluidizer, and standardizing to help to have a more consistent product before it is then passed through the membrane. In this part of the process, the option could be based on using a nanofiltration membrane or an ultrafiltration membrane to help in removing impurities from the dye product. This can be done by implementing what I'm going to be explaining later, which involves the addition of water, the process that we call dye filtration, to remove impurities before then concentrating the dye further to produce a concentrated and distorted product. And then the other options, as I explained before, is that the dye could be marketed in grain or solid state. So this part of the presentation gives you an overview of how the solid dye is being produced. This, of course, also comes through the first part of the process, which is the reactor, in which case we have the reactions undergoing between the components that make up the dye. This is then passed through a membrane system, which might involve the use of nanofiltration or ultrafiltration membrane. And obviously, if this is implemented, we are obviously taking out the other processes which involve the use of press. And then from nanofiltration or ultrafiltration membrane, the product is then passed to the standardizing to help to have a more consistent product before this is then passed to a spray dryer to get the final drain and desalted product. So one of the advantages that we need to look at by implementing the nanofiltration for this case is that it is possible, first and foremost, to increase the concentration of the dye product. So in most of the cases, the dye will be supplied at a lower concentration at the start. So possibly talking about maybe 5 to 7%. In some instances, we might be looking at 10% solid. And then using the membrane technology, we can pre-concentrate the solution up to 25 and sometimes even higher, higher than 25%, to then forward this to the spray dryer. What this means is that first and foremost, we are able to replace the press, which is mainly used by some companies. This helps to reduce the OPEX in terms of the operating cost. As we all know, press could mean having a higher energy consumptions due to the fact that it might be required to use a driving medium, either in either air or either vapor or steam, to help to complete the pressing stage. So if this is replaced with the membrane technology, we are able to reduce the operating cost, and also we are able to reduce the size of the spray dryer. So by significantly concentrating the dry at the start to 25%, and then this is forward to the spray dryer. So the production yield can also be increased by adopting membrane system for desalting. What that means is we are able to see a reduce in the percentage of dye loss with the membrane technology. If a press is used, normally you have a percentage of dye loss around the 10%. With the membrane technology, this can be reduced to below 2%, which is also beneficial with regards to the product recovery, or with regards to the sustainability of the process in overall. So implementing the membrane technology also helps to produce a more consistent dryer feed. And also it helps to reduce the process downtime due to the fact that it is possible to eliminate or to reduce the salt concentration in the process, which is then subjected to the spray dryer, which helps to reduce any sort of incrustations or blockage of the dryer noses. So this part of the presentation is to give you an example of dye filtration water requirement when we're talking about dye desalting when using some of the pre-selected membranes from PCI membranes. Normally, we have a number of membranes that we often use for dye applications when it comes to desalting. This could be based on using an ultrafiltration membrane, which is ES404, 4,000 Dalton cutoff, or using the AFC30 or AFC40, both of which are nanofiltration membranes. So the AFC30 is a negatively charged nanofiltration membrane in the region of 200 to 250 Dalton. The AFC40 is a nanofiltration membrane as well, which is in the region of 300 Dalton cutoff. Of course, this graphical representation that you can see in relation to the volume of the filtration water required to the percentage of salt removed, either when talking about monovalent salt or when talking about divalent salt. This representation is mainly referring to these three types of membranes, tubular. So the ES404, AFC30, AFC40. But of course, we PCI membrane also supply spiral membranes, which could be used for these types of process. We have a number of spiral membranes when talking about ultrafiltration or nanofiltrations with similar cutoff range that could also adopt similar concepts with regards to adding water, of course, the concept of dye filtrations to help to dissolve dye. So first and foremost, looking at the left-hand side with regards to monovalent salt that could be removed, so talking about sodium chloride, for example, by using either of these membrane, the amount of water that will be added varies to remove a certain percentage of salt from the solution. Of course, less water will be required when using the more open membrane type as to compare to the tightest membrane type, AFC30. But then, moving to the right-hand side, we can also look at the variation of water that's required to be added to the solution when there is a requirement to remove divalent salt. For example, calcium or calcium chloride or magnesium sulfate or many other salts that might be present in the solution. When it is required to remove the divalent salt, of course, the amount of water to be added is slightly higher compared to what's required for the monovalent salt. This is just an overview of what could be done with dye desalting. The amount of water to be used might vary depending on the type of dye that's been treated. Of course, we all know that there are different dye solutions available on the market. Either way, we can apply this concept to the requirement of the client to help to desalt their product. So the selection of these membrane types is based on the fact that the dye product itself could have a molecular weight that range between the 600 to 900 gram per mole. In some instances, it is possible that a bigger molecular weight could be encountered. This is due to the agglomeration of the monomer into DMS or polymers. We, as explained previously, we also have other types of ultrafiltrations or microfiltration membranes available that could be used for this application, depending on the sort of inquiry that the customer have. So this part of the presentation is to give you an overview of the dye filtration process. So obviously you have the reactor or the feed tank, in which case you have a solution of the dye that has got between 8 to 10% of salt, sodium chloride. There is also the presence of other salts within 1 to 2%. And then the dye content is between the 6 to 8%. So most importantly, the requirement is to reduce the salt to as much as possible within the final product. In this case, the filtration water is being added into the feed tank, which is then pumped through a membrane system. So it's either using an ultrafiltration membrane or a nanofiltration membrane, as we've discussed about earlier. For this particular case, the salt content in the concentrate was reduced to around 0.5%. So basically talking about the sodium chloride, for which the starting point was 10%. The sodium chloride was reduced to 0.5%. Other salt composition as well was reduced to around 1.5%. And then once the filtration process has been completed, so the amount of water added is stopped, then the same membrane system can then be used to concentrate the dye solution. So increasing the dye TS, total solid, from about 8% to 33%. This is the main concept with regards to the salting of the dye. But of course, this is also combined with the concentration of the dye. But it is also important to kind of place an emphasis on the water recovery from this process, because we are adding a significant amount of water to the system to remove impurities, to remove salt. To help with sustainability, it is important to help to establish a system that could recover the water that's been used. So we as PCI, we are also able to supply you a number of membrane systems. So either looking at a tubular configuration or looking at a spiral configuration, which could be implemented as the second stage to recover the water that's been used within this process. The selection of either tubular or spiral could depend on a number of factors, which could be in relation to the solid contents, which could be in relation to the nature of the dye, and many other factors. Either way, a reverse osmosis system could be used as a second stage to concentrate the permeate water that's been collected during the first stage, and then recover some of the dye that's been lost, or some of the salts or impurities which should be concentrated in the retintate. And then the permeate water collected from the reverse osmosis could then be reused as part of the dye filtration water, or could be reused as the main water supply for the production phase within the dye application itself. So this part of the presentation is to give you an overview of an example of percentage of dye loss when using some of the membranes technology that we use for the desalting process. So looking at the ES404, which is the 4,000 Dalton membrane, ultrafiltration membrane, which is the most open membrane when talking about this membrane type highlighted. So AFC 30, which is tightest, compared to the AFC 40. It is reasonable to see, let's say, the highest amount of dye loss when looking at the ES404 membrane type, because it's it's the most open, although it requires less water to be added to the solution when desalting. But then we're also seeing a very low passage or loss of dye with either the AFC 30 or the AFC 40. This is a reasonable amount of information in terms of passing this information to the client that the product loss is minimal while using the nanofiltration membrane. But at the same time, we are also able to remove the salt or other impurities from the solutions to help improve the quality of the final product. So this gives you an overview of the different types of dye that has been tested. So moving from Procyon red to Procyon yellow, Remson yellow, as well as giving you an indication of the percentage of dye that's been lost. In most of the cases, for the AFC 30, AFC 40, we are mainly below 1% loss. Okay, slightly higher dye loss is accounted for the ES404, but of course, this can also be recovered and reprocessed with the membrane technology. I'll be talking about this as well later on. So with one of the tests that has been completed on a dye product, I'm also able to show you the variation of the process parameter over time. So basically looking at the, let's say the concentrate conductivity, which is being recorded during the test, how this varies with time, as well as the permeate conductivity. What this shows is that at the start of the test, the feed streams or the reticulated or the concentrate conductivity, as the trial was mainly completed in a batch mode. The feed stream had a high conductivity, mainly due to the presence of salts or impurities in the solution. So the conductivity is high. So once a certain amount of water is being added to the solution, then all these impurities and salts are being washed out of the solution. So the conductivity decreases over time, which shows that all these components have been removed from the solution. But of course, what could be seen as well from the permeate conductivity, which is shown in green, is that the permeate that's been removed based on water and impurities high conductivity at the start, which of course reduces over time. As this reduces, this means that we are reaching a point where these impurities are removed or completely or almost completely. So just to like give you an overview of how the process varies with time. Of course, some samples are being collected during this time to analyze for salt contents or any other impurities as the process progresses. But for a quick overview, the conductivity of the solution in terms of the concentrate as well as the permeate could be used as an indication to see how the process behaves, to understand if the additional water to the process has helped to remove salt and impurities from the solution. So this is a typical process variation that should be encountered when completing a filtration for the sorting process. On the right-hand side, you can see a variation of the flux in terms of the volumes of permeate produced per hour in relation to the membrane area over time. Of course, the first stage of the process is mainly based on that filtration, in which case the flux of the system is more or less constant. Of course, reduces when the process progresses, and once that filtration is completed, then the concentration phase is started. This, of course, is normal to see a reduction in flux over time as the product is concentrated, for example, from 7% to 25%, as we have seen previously in the presentation. So this gives you an overview of what could happen when completing a dye filtration process and concentration of the dye solution over time. So the final stage of the presentation is to show you the other type of application that's important within the textile industry. As we all know, there is a significant amount of pollutants that are mainly produced within this industry. So mainly talking about the chemical oxygen demand, color, and other impurities. Depending on where the textile production is happening, talking about Europe, Asia, or Africa, there are a number of local regulations that applies to this industry with regards to the limit of the sort of impurity that could be discharged into the local sewage and so on. So this process gives you an overview of what could be done to improve the process. So from textile wastewater, this wastewater effluent could be passed through a biological treatment, which of course is not part of what PCI can supply for the time being. Following a biological treatment, the effluent water could then be passed through an ultrafiltration system to remove any residual solids and so on. It is important to place an emphasis on this two sections in terms of the biological treatment and the ultrafiltration treatment process. There might be some other technology, of course, there are other technologies available that could be used for the textile wastewater. This could be looking at the soft air flotation, or looking at the use of ozone or ultraviolet for the treatment of this wastewater. But from our side, with regards to the work to be done from PCI, the incorporation of biological treatments together with ultrafiltration, as I've explained before, we have a number of membranes that could be chosen from. So either using the hollow fiber membrane that we can supply from PCI, or you can also implement the use of the A series membrane, mainly looking at the A8 membrane config system that could be used as a side stream MBR for these applications. So this wastewater from the textile industry could be processed in combination with biological and ultrafiltration to produce an effluent which has less solids, sludge. And then this effluent could be passed through a reverse osmosis membrane. Of course, from PCI membranes, we have a number of membrane configuration, as explained previously, either utilizing the tubular membrane or utilizing a spiral membrane. We have reverse osmosis options available for these two configurations to treat the effluent from the ultrafiltration in order to produce a permeate stream, which basically is pure enough to be reused as part of the textile process itself. So the permeate produced from the reverse osmosis basically has no salts. The COD content is minimal. Of course, it depends on what's causing the COD in the production phase. If this is of alcohol origin, it is likely that the COD will pass. Some COD will pass, but in this case, the COD is mainly due to the organic constituent of the dye. So we have a very high retention of the COD, and therefore a low passage of the COD into the permeate stream. For this particular case, the recovery rate of the reverse osmosis was in the region of 55% recovery. So a significant recovery of the water stream. And in the same instance, the COD in the concentrate of the reverse osmosis was in the region of 600 milligram per liter. And the color of the concentrate of the reverse osmosis was in the region of 500 milligram per liter. So these are specifications that are not acceptable for this particular client with regards to discharge. Therefore, the concentrate itself could then be reprocessed with another membrane system, in this case using a spiral membrane, so a FG spiral core LCR NF, which is a nanofiltration membrane, which is further used to process the concentrate deriving from the reverse osmosis. So the concentrate is processed to achieve a 90% recovery of the water from this process, in which case the COD from the concentrate itself is also reduced further in the permeate to about 80 to 90 milligram per liter. This also allowed to have a color in the permeate from this stage around the 30 to 40 milligram per liter. At the same time, the salinity, the water produced, the permeate produced from the nanofiltration membranes has a salinity, some salt content, but of course, the water has been treated containing salts, but this could also be used as part of the production process where required. At the same time, a concentrate is produced from the nanofiltration, which has a significant amount of COD as well as color. This could be, of course, returned back into the starting process within the biological treatment and the US stage to reprocess. In overall, what we're trying to show over here is that with the membrane technology in combination with a biological treatment, in this case, it is possible to recover a significant amount of pollutants from the stream. It is possible to reduce the impurities that might be discharged at a later stage, and also it is possible to reuse processed water that's been produced from the combinations of this membrane technology. So what could be seen from here with regards to COD and color rejection is that we have about 80 to 85% COD rejection when talking about the rejection rate as to compare to the inlet from the concentrate of the reverse osmosis to the outlet in the nanofiltration. And also the color rejection is in the region of 93%, which is a significant reduction with regards to the impurities in this case. As explained previously, we have a number of membrane that we can supply from PCI membrane. So basically, either looking at the A series membrane that could be used as a side stream MBR, or selecting holofiber membrane itself for the submerged MBR systems. As well, a selection of reverse osmosis from our side and nanofiltration membranes are available for these processes. So we could either be looking at a tubular configuration, so talking about AFC 80 or AFC 99, or we could be talking about the spiral membranes reverse osmosis available from PCI. Same applies as well for the nanofiltration membrane. So that's the end of this presentation. Thank you everyone for taking part in this. And we can now look at the question and answer section.
Thank you for this great presentation. So I have some questions. Since you were introducing us different types of membranes, so my first question is, what are the benefits and disadvantages of using tubular membranes in comparison with the spirals for that application?
Okay, thank you so much for the first question. Of course, we need to try to understand, what are the differences between the tubular and also the spiral membrane configuration. First and foremost, the tubular membranes are they call open channel, which allow them to be used with a certain crossflow velocity, which helps to introduce the so-called scouring effect within the diameter of the tubes that reduces the fouling potential over time with the membranes. So the tubular as well could also be used for ice solid applications, which is not something really applicable to spiral membranes themselves. Of course, tubular membranes have got, with regards to footprints, they've got a lower membrane area as to compare to the footprints. However, the spiral membrane has got a high membrane area, when it comes to the footprint. At the same time, spiral membranes they require a significant purification in most of the cases, which is not the case for tubular membrane. However, when we're talking about the application, as I was explaining before, with regards to having a tubular ES404, AFC30, or AFC40 membranes, the dye solution could be used within this in different situations. Could be used with the tubular configuration, but it can also be used with the spiral configuration only if the dye has a low amount of some solid, and also only if the dye hasn't got the ability to precipitate. So if the dye could precipitate, then it might not be the case of utilizing spiral configuration for these applications. So this are more or less, let's say, the benefits and advantages of using either of this configuration.
Very interesting. Thank you. Then my second question is, do you have experience with processing other types of dye besides reactive dye with membrane technology?
Well, of course, we have shown over here a number of dye that that's been processed with our membrane technology. Reactive dye, I think, from my understanding, is the mostly used type of dye within the industry due to its ability to form a covalent bond with the fibers or the material to which it's been applied. Other type of dye, as explained previously, could also be processed with our memory technology. Of course, the studies, the trial testing will have to be completed on this other type of dye. We have a number of membranes available that we could test, and we could evaluate the properties of this dye with the membrane systems. So yeah, you can also use this memory technology for other type of dyes.
Thank you. Thank you for your answer.
You're welcome. Okay, I believe there are no other questions, and yeah, thank you everyone for taking part in this webinar. And yeah, we are also looking forward to working with you in the future. If you have any applications or projects that may require our support, our technology, we are more than happy to talk to you. We are more than happy to present our solution to you. And we are looking forward to working with you in the future. Thank you, everyone. Bye-bye.